Calculating wind turbine electricity production for each month of the year helps to make the right choices when it comes to investing in residential wind energy. There are several factors which a homeowner must consider when deciding whether to invest in a wind generator for their property. Cut-in speed, or starting wind speed, shows the point at which the wind turbine starts to produce electricity. If the wind speed is lower than the cut-in speed, no electricity is generated. Typically, the cut-in speed of wind turbines designed for domestic use varies from 2.2 to 4.5 meters per second. Rated speed defines at what speed a wind turbine will produce the amount of power it is quoting in its name. The rated speed of a turbine depends on its size but is usually within the range of 6.7 to 22 meters per second. There are different kinds of wind turbines. They can be divided according to the position of their axis and how they are mounted to be elevated above the ground. Whether a turbine will be connected to the electric grid needs to be decided before selecting the needed size. Horizontal axis wind turbines produce more power but are more expensive and make more noise. In contrast, vertical axis turbines are less noisy, but they are less efficient and more difficult to maintain because turbine parts are not easily accessible. Turbines that can be mounted on the roof are cheaper and easier to install, but they do not produce as much electricity as pole-mounted turbines, which, however, are much more expensive. Also, local planning rules must be considered. A wind turbine can operate in sync with the electricity grid. A grid-connected wind turbine can help reduce the consumption of electricity supplied by utilities, thereby reducing costs or even producing profits. Grid connection ensures stable electricity supply. If grid connection is not practical or desired, the supply stability must be augmented through diversification of production, for example, by using a hybrid solar-wind production and considerable storage facility. Each turbine has a different power output for different wind speeds. These values are shown on the power curve that is included in the technical documentation for each turbine. Let's take a generalized curve of a small wind turbine as an example. It is also worth paying attention to the fact that when talking about the power of the turbine, we mean the electrical power, not the mechanical, and such criteria as turbine efficiency refers to how much mechanical power has been converted into electrical power. In order to calculate how much energy a wind turbine can produce in a month, we also need to understand what wind speeds prevail in our location. For the calculations, we use location intelligence report obtained from @c.fi. The handy paginated PDF contains all key environmental and climate data for our specific location as easily understandable statistical distributions. Such reports are available for every location in the world. One of the graphs in the @c report shows wind speeds by month. It is clear from the graph that wind speeds vary considerably throughout the year, something that we must consider particularly for off-grid systems. To calculate the electricity production of a wind turbine, we use a table with probabilities of various wind speed brackets for each month, which is also included in the @c report. Let's consider this power curve we've mentioned before and wind distribution to calculate how much energy our wind turbine can produce per month. For the calculation, let's assume that our turbine has the following characteristics: 7 kilowatts peak output, 3 meters per second cut-in wind speed, 9 meters per second rated speed. The amount of energy generated is equal to the power output multiplied by the time the turbine operates at that power output. The time the turbine operates at a particular power output is determined by the probability distribution of wind speeds. For the calculation, we will use the table which shows the probability in percent of wind in various speed ranges for each month. For example, in December, the probability of wind ranging from 9 to 11 meters per second is 18%, and all ranges with higher values account for 10%. Since the rated speed of the turbine is 9 meters per second, we see that the turbine will operate at its rated power of 7 kilowatts during the 28% of the total running time. Let's calculate how much electricity our wind turbine will generate in December during the time it runs at its rated power. We need to convert the amount of time the turbine runs at its rated power into a decimal and then multiply that number by the number of days in the month and the number of hours in a day. After that, we need to multiply the obtained number by 7 kilowatts, the rated power of our turbine. We see that the wind turbine will generate 1,456 kilowatt-hours of energy during the time it runs at its rated power. So we have calculated the amount of electricity that a wind turbine will generate when it reaches rated speed. Although wind speeds, which are less than the rated speed but above the cut-in speed, will generate less power, it still will be a significant amount of power. Let's calculate how much electricity is produced in the remaining sections of the curve, where wind speeds are above the cut-in speed but do not reach the rated speed of the turbine. For example, at wind speeds of 3 to 5 meters per second, approximately 1 kilowatt of energy is produced, and so on. To calculate the amount of energy that will be generated in December, by wind speed brackets from 3 to 9 meters per second, we need to multiply the probability of wind, converted into a decimal fraction, by the power output corresponding to that speed bracket. Then we need to add the results for each speed bracket, and multiply the obtained number by the number of days in a month and the number of hours in a day. Thus, the amount of energy that the wind turbine will produce during the time when it doesn't reach its rated power will be 1,859 kilowatt hours. Altogether, the example turbine is expected to generate an average of 3,316 kilowatt hours each December. We can repeat the calculation for all other months. Here we use Excel for convenience. For example, July will generate less than half compared to December. 1,616 kilowatt hours. The average annual electricity production of the example 7 kilowatt turbine mounted in our specific location would be 30 megawatt hours, which, with an average cost of electricity of 20 cents per kilowatt hour, translates to $6,000 worth per year. If it is enough to justify the costs of purchasing, installation and annual maintenance depends on the costs and yields of available alternatives. Let's talk about impact of other factors. In addition to the wind speed, one has to consider the typical direction of the winds. Let's take a look at the wind rows provided in the at-sea report for our location. This graph shows that the predominant wind directions are south and southwest. This is important to consider when choosing the place where the wind turbine will be installed to ensure there are no large obstructions in the path of the wind. Another important aspect is the terrain profile. Elevated locations are preferred, whereas land depressions might lead to significant performance losses. As visible from the elevation model in our at-sea report, our location is slightly elevated, but there are higher hills to southwest about 6 kilometers away, which should be enough distance not to impact our turbine too much. Thus, to assess the feasibility of installing a wind turbine, not only the parameters of the wind turbine itself must be taken into consideration, but also environmental parameters such as the probability distribution of wind speeds, wind direction, and the local terrain. Thus, before making any investment decision, detailed local data should be consulted, and any technological choices based on evidence. There are plenty of choices when it comes to wind turbines. And a tiny upfront investment in a location intelligence report can significantly increase the returns and reduce the risk of misinvestment. If you're interested in learning more about how environmental data can be used in different scenarios, press the subscribe button to see more videos and insights from our Analytics PyCon team.